Alrighty guys, here's what we're going to do is we're going to talk about two things in this third part of this video. One of that being talking about some more graphs and then talking about power. So the first thing I'm going to do is talk about that law of conservation of energy still and talk about graphs. One thing I have seen every once in a while, that the law of conservation of energy, where your energy initial equals energy final, or total energy is conserved. I have seen this come out in a couple different ways, and that can be shown with some graphic representations. If I were to draw a graph, and let's say this graph represented energy and time. And let's say my system is, let's go use that pendulum as an example. So my pendulum is swinging back and forth. All right. If my pendulum is swinging back and forth, what is going on overall? Well, my system is total energy stays the same. So what I'm going to do is a nice dotted line across the top. We're going to do total energy stays the same. If we were to look at time as time goes on, we would see that my energy starts all potential. And so let's do potential as a pink color or pinkish color. So all my energy starts as potential. And then that potential energy then turns into 0, then goes up to kinetic. And that being because this is parabolic shape is because gravity affects it more towards the end of the swings rather than down in the middle. Which means if I'm looking at kinetic energy, let me say potential is that pinkish color. Let's call kinetic energy orange. That means kinetic energy starts at 0 and then at some point goes to 100% and then ends at 0. And that is because whatever happens as far as my total energy is concerned is if you add both of these graphs together at any point, you should have 100% of your energy still involved. One thing that does get a little bit tricky and interesting is that your 50-50% ratio is not halfway between, I would say, call this T1/2 and this T. It is somewhere before then because these are parabolic relationships. So notice that this isn't at the 50% mark. We'll call this T1/4. It's sometime before then. And this is sometime after T equals 3/4. All right. Now what I'm going to do is switch gears a little bit and talk about power. So power is written as, let's do a little bit of a darker color here. Power is written as the change in energy over time. This can also be written as, usually as work over time. And we're going to do a little bit of derivation here in a second on why it also equals force times velocity. The unit for power, so this is power, is how quickly work is being done. So how quickly work is being done. And the units for this is watts, or sometimes can be written as joules per second, or sometimes written as Newton meters per second, because a Newton is force, velocity is meters per second. I rarely ever see it written like this. You more see it written as watts or joules per second. And what I'm going to do is now talk about power and the couple things that I've seen about it. Power, due to it's called a change of energy over time, power is never going to be a negative number is always going to be positive. And how do I get this derivation right here? Well, for example, let's say if an object, its change in energy is all potential. So that means the change in energy is all potential energy over time. Well, change of potential energy be mgh over t, where gravity is an acceleration. What we know, mass times gravity, or mass times acceleration, that is force. So these first two pieces right here, I would say this right here, is force. And then what we have as far as velocity goes, and that's going to be height times time, or height divided by time, or some distance divided by time. That is velocity. This equation is not given to you, but sometimes it'd be nice to have in your back pocket when it comes to calculating power. Whenever you see power, note power is the change in energy over time, and then think about this equation from time to time. If what you're given right here just doesn't give you quite the information, you might need to use force times velocity. Alrighty, I'm going to call a pause on that video, and then we're going to continue on with the next piece, looking at some special cases with work and energy. Alrighty, instead of coming on the next video, let's actually just continue to work right here. I do have about 11 minutes left on this video before the cutoff would be there, so I think I can squeeze a little bit more in. One thing I'm going to talk about is some relationships. If I were to look at relationships in energy, could I make a graph very quickly of looking at, let's say, kinetic energy to velocity? And that would be k is proportional to velocity squared. How did I do that? Well, you take this equal sign, you can throw a proportionality symbol in there, and then knock off anything else you don't need in your relationship, and you can say the kinetic energy of an object is going to be equal to its velocity squared. So if I were to make a graph of kinetic energy versus velocity, what you would find out is that as your velocity increases, your kinetic energy looks a little bit like this. Now, if we wanted to linearize that data, what we could do is look at kinetic energy and then do a velocity squared. And that would be more of a straight line graph right here. If we were to look at potential energy, so potential energy, and compare that to height, we'd say potential energy is proportional to height. And all you would say is potential energy and height carry a linear relationship.